Hello, students, and welcome to the class. We'll begin our class by thanking God for the gift of this day and ask His blessings to start our studies. We begin with the second chapter in Science 1, Periodic Classification of Elements. We first revise the topics which we had studied in the previous classes. Matter. Matter is anything that has mass and takes up place. The different types of matter are solids, liquids, gases, plasma. The smallest particle of matter is called an atom. Elements are substances made from only one type of an atom, and the different types of elements are metals, nonmetals, metalloids. We have also studied the difference between the molecules of an element and the molecules of a compound. All the atoms of an element are same. For example, the molecule of oxygen, hydrogen, etc. Whereas the molecule of compounds have atoms of different elements. For example, water. We now study the classification of elements in details based on their properties. Today, 118 elements are known to the scientific world. Around the year 1800, only 30 elements were known. As more and more elements were discovered, scientists studied the patterns and properties in the available information, and the elements were classified into three main groups: metals, nonmetals, and metalloids. As the knowledge about elements and their properties went on increasing, different scientists started trying out different methods of classification. The first scientist to classify elements on basis of their properties was Dobrener. In the year 1817, a German scientist Dobrener suggested that properties of elements are related to their atomic masses. He made groups of three elements each having similar chemical properties and called them triads. He arranged the three elements in a triad in increasing order of atomic mass and showed that the atomic mass of the middle element was approximately equal to the mean of the atomic masses of the other two elements. For example, if you take the triad lithium, sodium, potassium, the first element lithium has actual atomic mass 6.9. The third element potassium has atomic mass 39.1. If you take the mean of the two, it comes as 23, which is the actual atomic mass of sodium. However, all the known elements could not be classified into Dobrener's triads. Next, Newland's law of octaves. In the year 1866, Newlands arranged the elements known at that time in an increasing order of their atomic masses. He started with the lightest element, hydrogen, and ended up with thorium. He found that every eighth element had properties similar to those of the first. For example, sodium is the eighth element from lithium, and both have similar properties. Also, magnesium shows similarity to beryllium, and chlorine shows similarity with fluorine. Newlands compared this similarity with the octaves in music. He called the similarity observed in the eighth and the first element as the law of octaves. Thus, Newland's law of octaves states that when the elements are arranged in increasing order of their atomic masses, the properties of the eighth element are similar to that of the first. However, many limitations were found in Newland's octaves. This law was found to be applicable only up to calcium. Newlands fitted all the known elements in a table of 56 boxes And so he placed two elements each in some boxes to accommodate all the known elements in the table. For example, cobalt and nickel. Moreover, he placed some elements with different properties under the same note. For example, Newlands placed the metals cobalt and nickel along with halogens, while iron, having similarity with cobalt and nickel, was placed away from them with the nonmetals oxygen and sulfur. Also, Newland's octaves did not have provision to accommodate the newly discovered elements. The properties of the new elements discovered later on did not fit in the Newland's law of octaves. Mendeleev's periodic table. The Russian scientist Dmitry Mendeleev developed the periodic table of elements during the period 1869 to 1872 AD. Mendeleev's periodic table is the most important step in the classification of elements. Mendeleev considered the fundamental property of elements, that is, the atomic mass, as standard and arranged 63 elements known at that time in an increasing order of their atomic masses. He organized the periodic table on the basis of the chemical and physical properties of the elements. These properties were the molecular formulae of hydrides and oxides of elements, their melting points, boiling points, densities, etc. Hydrides means a chemical compound formed by a chemical compound in which hydrogen is combined with another element, and oxide means a chemical combination of oxygen and one other element. On the basis of his findings, Mendeleev stated the following periodic law. Properties of elements are periodic functions of their atomic masses. While applying the law that the properties of elements are a periodic function of their atomic masses to all the known elements, Mendeleev arranged the elements with the thought that the information available till then was not final, but it could change. As a result of this, the Mendeleev's periodic table demonstrates the following merits. First, the atomic masses of some elements were revised to give them proper place in the periodic table according to their properties. For example, the previously determined atomic mass of beryllium 14.09 was changed to the correct value 9.4 and beryllium was placed before boron. Second, Mendeleev kept vacant places in the periodic table for elements not discovered till then. Three of these unknown elements were given the names Eka boron, Eka aluminium, and Eka silicon, and their atomic masses were indicated as 44, 68, and 72 respectively. Their properties were also predicted. Later on, these elements were discovered and named as scandium, gallium, and germanium respectively. The properties of the elements matched well with those predicted by Mendeleev. Third, there was no place reserved for noble gases in Mendeleev's original periodic table. However, when noble gases such as helium, neon, argon were discovered towards the end of 19th century, Mendeleev created a zero group without disturbing the original periodic table in which the noble gases were fitted very well. But we also see a few demerits of the Mendeleev's periodic table. First, the whole number atomic mass of elements, cobalt and nickel, is the same. Therefore, there is an ambiguity regarding their sequence in Mendeleev's periodic table. Second, isotopes were discovered long time after Mendeleev put forth the periodic table. As isotopes have the same chemical properties but different atomic masses, a challenge was posed in placing them in Mendeleev's periodic table. Third, when elements are arranged in an increasing order of atomic masses, the rise in atomic mass does not appear to be uniform. It was not possible, therefore, to predict how many elements could be discovered between two heavy elements. Fourth, the position of hydrogen. Hydrogen shows similarity with halogens. For example, the molecular formula for hydrogen is H2, while the molecular formula for fluorine and chlorine are F2 and Cl2. In the same way, there is a similarity in the chemical properties of hydrogen and alkali metals. There is a similarity in the molecular formulae of the compounds of hydrogen alkali metals with chlorine and oxygen. On considering the above properties, it cannot be decided whether the correct position of hydrogen is in the group of alkali metals or in the group of halogens. Modern periodic law. After the discovery of electron, scientists started exploring the relation between the electron number of an atom and the atomic number. The atomic number in the Mendeleev's periodic table only indicated the serial number of the element. In 1913 AD, the English scientist Henry Moseley demonstrated with the help of experiments that atomic number of an element corresponds to the positive charge on the nucleus or the number of protons in the nucleus of the atom of that element. This revealed that atomic number is a more fundamental property of an element than its atomic mass. Accordingly, the statement of the modern periodic law was stated as properties of elements are a periodic function of their atomic numbers. The classification of elements resulting from an arrangement of the elements in an increasing order of their atomic numbers is the modern periodic table. The properties of elements can be predicted more accurately with the help of the modern periodic table. The modern periodic table is also called the long form of the periodic table. In the modern periodic table, the elements are arranged in accordance with their atomic number. As a result, most of the drawbacks of Mendeleev's periodic table appear to be removed. However, the ambiguity about the position of hydrogen is not removed even in the modern periodic table. Structure of modern periodic table. The modern periodic table contains 7 horizontal rows called periods and 18 vertical columns called groups. The arrangement of periods and groups result into formation of boxes. Atomic numbers are serially indicated in the upper part of these boxes. Each box corresponds to the place for one element. Apart from these 7 rows, 2 rows are shown separately at the bottom of the periodic table. These are called lanthanide series and actinide series respectively. There are 118 boxes in the periodic table, including the 2 series. It means that there are 118 places for elements in the modern periodic table. The entire periodic table is divided into 4 blocks: S block, P block, D block, and F block. The S block contains the groups 1 and 2. The group 1 elements of the S block are called alkali metals, and the group 2 are called as alkaline earth metals. The groups 13 to 18 constitute the P block. The P block contains the halogens. The group 3 and 12 constitute the D block. The D block elements are called transition elements, while the lanthanide and actinide series at the bottom form the F block. The F block elements are called as inner transition elements. A zigzag line can be drawn in the P block of the periodic table. The three traditional types of elements can be clearly shown in the modern periodic table with the help of these zigzag lines. If we see the modern periodic table carefully, we can see that the metalloid elements lie along the border of the zigzag line. All the metals lie on the left side of the zigzag line, while all the non-metals lie on the right side. Modern periodic table and electronic configuration of elements. Within a period, the neighboring elements differ slightly in their properties, while distant elements differ widely in their properties. Elements in the same group show similarity and gradation in their properties. Gradation means a change taking place through a series of stages in a gradual manner. These characteristics of the groups and periods in the modern periodic table are because of the electronic configuration of the elements. It is the electronic configuration of an element which decides the group and the period in which it is to be placed. Groups and electronic configuration. The number of valence electrons in all the elements from the group 1, that is the family of alkali metals, is the same. While going from top to bottom within any group, one electronic shell gets added at a time. From this, we can say that the electronic configuration of the outermost shell is characteristics of a particular group. However, as we go down a group, the number of shells goes on increasing. Periods and electronic configuration. While going from left to right within the period, the atomic number increases by 1 at a time, and the number of valence electrons also increases by 1 at a time. We can say that the elements with the same number of shells belong to the same period. In the modern periodic table, electrons are filled in the same shell while going along a period from left to right, and at the beginning of the next period, a new electron shell starts filling up. The number of elements in the first 3 periods is determined by the electron capacity of the shells and the law of electron octet. As per the electron holding capacity of shells, 2 elements are present in the first period and 8 elements in the second period. The third period also contains only 8 elements due to the law of electron octet. There are a few more factors which control the filling of electrons in the subsequent periods. For example, if we take the shells K, L, M, N, N is the number of shell. The formula for filling the electrons in the shell is 2n square. So in the K shell, we can fill 2 into 1 square, that is 2 electrons. L can have 2 into 2 square, that is 2 into 4, which is 8 electrons, and so on. For example, if you take the example of potassium, the atomic number is 19. Its electronic configuration will be 2881. That means in the first shell, it can have 2 electrons. Second shell, it can have 8 electrons. Third shell, even if its capacity is 18, but on filling 8 electrons, the octet is complete, and therefore the next electron will go and into the next shell. So that is what we mean by there are other different laws which are also taken into account for filling of the shells. Next, periodic trends in the modern periodic table. When the properties of elements in a period or a group of the modern periodic table are compared, certain regularity is observed in their variations. It is called the periodic trends in the modern periodic table. In this standard, we are going to study few out of it. The first one is valency. Valency of an element is determined by the number of electrons present in the outermost shell of its atom, that is the valence electron. Valence electron means the electron which is present in the outermost orbit of the atom. Atomic size. The size of an atom is indicated by its radius. Atomic radius is the distance between the nucleus of the atom and its outermost shell. The unit for atomic radius is picometer and it is smaller than the nanometer. Atomic radius goes on decreasing while going from left to right within a period. The reason behind this is as follows. While going from left to right within a period, the atomic number increases by 1, meaning the positive charge on the nucleus increases by 1 unit at a time. However, the additional electron gets added to the same outermost shell. Due to the increased nuclear charge, the electrons are pulled towards the nucleus to a greater extent and thereby the size of the atom decreases. While going down a group, the atomic size goes on increasing. This is because while going down a group, a new shell is added. Therefore, the distance between the outermost electron and the nucleus goes on increasing. As a result of this, the atomic size increases in spite of the increased nuclear charge. The metallic and non-metallic character. The metallic elements like sodium, magnesium are towards the left. The non-metallic elements such as sulfur, chlorine are towards the right. The metalloid elements, silicon, lies between these two types. The zigzag line separates the metals from non-metals in the periodic table. Elements appear to have arranged in such a way that the metals are on left side of this line, non-metals are on the right side, and metalloids are along the border. It is seen from the chemical formulae of simple ionic compounds that the cation in them is formed from a metal while the anion is formed from non-metal. This is based on the electronic configuration. If we see the electronic configuration of metals, they have usually less than 4 electrons in the outermost shell, and as a result they have a tendency of giving the electron to have a complete octet and a stable ion. On the other hand, the non-metals, they have more than 4 electrons in their outermost shell. As a result, they have a tendency to accept the electrons and thus form an anion, which is a negative ion. Hence, all the electrons in an atom are held by the attractive force exerted on them by the positively charged nucleus. Electrons in the inner shells lie in between the valence shell and the nucleus. Because of their presence, the effective nuclear charge exerting an attractive force on the valence electrons is somewhat less than the actual nuclear charge. Thus, the number of valence electrons in metals is small. Also, the effective nuclear charge exerting attractive force on the valence electrons is small. As a combined effect of these two factors, metals have a tendency to lose the valence electrons to form cations having a stable noble gas configuration. This tendency of an element is called electropositivity, and it is the metallic character of that element. The periodic trend in the metallic character of elements is clearly understood from their position in the modern periodic table. While going down a group, a new shell gets added, resulting in an increase in the distance between the nucleus and the valence electrons. This results in lowering the effective nuclear charge and thereby lowering the attractive force on the valence electrons. As a result of this, the tendency of the atom to lose electrons increases. Also, the penultimate shell becomes the outermost shell on losing valence electrons. The penultimate shell is a complete octet. Therefore, the resulting cation has a special stability. Due to this, the tendency of the atom to lose electrons increases further. The metallic character of an atom is its tendency to lose electrons. Therefore, the following trend is observed. The metallic character of elements increases while going down the group. While going from left to right within a period, the outermost shell remains the same. However, the positive charge on the nucleus goes on increasing while the atomic radius goes on decreasing, and thus the effective nuclear charge goes on increasing. As a result of this, the tendency of atom to lose valence electrons decreases within a period from left to right. The two factors, that is, the increasing nuclear charge and decreasing atomic radius as we go from left to right within a period, are responsible for increasing the effective nuclear charge. Therefore, the valence electrons are held with greater and greater attractive force. This is called electronegativity of an atom. Due to increasing electronegativity from left to right within a period, the ability of an atom to become anion by accepting outside electrons goes on increasing. The tendency of an element to form anion or the electronegativity is the non-metallic character of an element. Gradation in halogen family. The group 17 contains the members of the halogen family. All of them have the general formula X2. For example, if you take chlorine, its molecular formula is Cl2, fluorine F2, bromine Br2, iodine I2, etc. A gradation is observed in their physical state down the group. Thus, fluorine, chlorine are gases, bromine is a liquid, and iodine is a solid. Here we come to the end of the chapter. Students, you all are requested to read the lesson carefully and answer the assignments given after this topic. Thank you.